So hi everyone, my name is Ruben. I'm an SRE working in Google Maps and based in New York. And today I'm presenting the case of the Misnamed series, a cast analysis of Google Maps, a Google Maps incident. At the end of this talk, you will have learned how CAST, which stands for Causal Analysis based on systems theory, produced deeper insights and better recommendations than the postmortem that was conducted for this incident, which was based on root cause analysis, or RCA. So I will talk about, in this talk, I will describe the incident at a high level, how our users were affected, what the root cause analysis found, and what things it recommended, a brief high-level introduction to accident models, what the CAST analysis found and what things it recommended, and a comparison between the two methods, showing that CAST was more impactful than the RCA for this particular incident. And I will end the presentation with my key takeaways and a few additional resources. So let me start describing the incident and what our users experienced. So in the summer of 2024, we started to receive user reports about incorrect US city names, and these cities had the word balance in parentheses added to the end of the city name. So imagine this year I'm going to the Kentucky Derby Festival happening at Louisville, Kentucky. I get in the car, search for Louisville in Google Maps, and I'm shown Louisville, Jefferson County, Metro Government balance. Now I'm utterly confused. Is this the real Louisville? What if I arrive there and it's not? So I'm really frustrated. So once we knew on our end, we reverted those bad city names back to their correct names. And this is the high-level order of events of the incident. The US Census Bureau published a data set containing information of cities in the US, like their names, their geographical areas. This data set included the balanced names for some cities instead of their official names. Why balance? So when a city grows, like in the case of Indianapolis, for example, sometimes it surrounds other smaller places, and all these places together are still called Indianapolis. This is what you see in the green boundary. And for statistical purposes, the US Census Bureau maintains the geographical area of the original city, which they call balances. This is highlighted in orange. And there are a total of 9 of these balances in the US, and the US Census Bureau included all these 9 balances in their data set instead of the official names. Now, an internal team looked at this data set, trying to find problems with the data. They did not find any problems with the data set, so we published the data set to Google Maps. The impact on our users started. The users started to report the misnamed cities in several states. And as part of the response to the incident, we started to manually fix the city names in the database. In parallel, we initiated an automated rollback of the dataset. And eventually, all the misnamed cities were fixed, and the impact on our users ended. Finally, a postmortem based on root cause analysis was written. Now, I will show you what the RCA, the root cause analysis, found and what improvements it proposed. And my goal with this is to show you later what CAST found, so that we can compare both methods as they were applied to this particular incident. So I want to pause for a moment to mention that when we consider an external data set to be imported to the map, a team of geospatial data specialists evaluates the data set, searching for incorrect data. They use an internal specialized evaluation tool, and they also follow a policy that is set by a separate team called the data import team that defines the procedure to follow during their evaluation. And if the geospecialists find any problem with the data set, then they flag those problems, and a decision is made whether to move forward with the data set import or not. Now, as I mentioned earlier, the US Census Bureau published a dataset containing city names and their geographical areas for all 50 states. The team of geospecialists selected and evaluated 4 states, those that you can see here in dark green: California, Washington, Texas, and New York. They didn't find any problems in any of those 4 states. The RCA also found that 6 states, those that you can see here in red, contain the misnamed cities, of which here you can see 3 examples. And it turns out that the geodata specialists did not evaluate the data for any of those 6 states. I'll tell you in a bit what explanation the RCA, the postmortem, gave for that. The RCA came up with 2 root causes. The first was a limited evaluation tool. The RCA found that the tool used by the geospecialists did not support the detection of incorrect city names. The RCA proposed action items, recommendations, to address this limitation of the evaluation tool. The first one was to automate the detection of naming issues in cities. The second one was to write instructions on how to enable specific checks in the tool. And the third one was to flag special characters such as double quotes, parentheses, etc. And lastly, to implement programmatic checks to block the publication of large data sets that have naming issues. The second root cause was ad hoc sampling of states. They chose Washington, California, Texas, and New York for the evaluation, as we mentioned. But why not evaluate the data for the 50 states? Well, 3 reasons. First, the data set for the entire country was too large for the geospatial team to evaluate. Second, the dataset import policy they had to follow did not provide guidance for sampling states. And the third one, the people in the team lived in those 4 states, so they had local expertise to evaluate the data for their home states. But as we saw earlier, these 4 states did not include any of the states that contain misnamed cities, those in red. Historically, the team had followed a thorough evaluation process, so this second set of action items or recommendations was meant to increase the effectiveness of the existing evaluation process. The first recommendation was to evaluate prominent cities like Indianapolis, Nashville, etc. The second one was to codify a process for flagging substantial differences in city names and send those for manual review. The third one was to assemble a virtual team to review high-impact datasets that can affect the search functionality in Google Maps. This was the summary of the root cause analysis. Now, before showing you the cast analysis, let me introduce the concept of accident model. So, an accident model explains why incidents happen. Like any model, an accident model is an abstraction in which we consider some aspects of an incident more relevant than others. The traditional and most common accident model is linear causality. So you place a series of events into a chain, with each event causing the next one. Many methods like the Swiss cheese model or the 5 whys are based on this accident model. And all these methods use different visual representations for an event chain, but they share the same focus, which is to identify the causal relationships between events that ultimately lead to an incident. There is another accident model that is based on systems theory. CAST is based on this accident model. Instead of a chain of events, it focuses on modeling the adaptive behavior happening in the system. In this model, the cause of an incident is a system that allows, enables, and safe decisions to happen. Instead of a chain of events or a series of Swiss cheese slices, this accident model uses control feedback loops to model behavior happening in the system. And I will describe in a bit what a control feedback loop is. So if our accident model explains why incidents happen, then it follows that the model will also inform our approach to preventing incidents. The biggest problem with linear causality is that it finds simple explanations to complex incidents. One can always place events into a timeline because events happen at some point in time, but that does not necessarily mean that if an event happens before another, the first causes the second. And as an example, let's focus on the event dataset with misnamed series passes evaluation, which causes the dataset published event. One cause found in the RCA, as I mentioned, was that the geospecialists missed the states containing misnamed cities. Linear causality assumes that if the first event cannot happen, then the following event cannot happen either. Therefore, if the geospecialists identify the states containing misnamed cities, then the dataset won't pass the evaluation. In other words, the assumption in the RCA is that if we ensure that the geospecialists identify the states containing misnamed cities, then the chain of events is stopped and the incident cannot happen. So, and then no dataset containing misnamed cities will pass the evaluation. That is the reason the RCA proposed action items around increasing the effectiveness of the evaluation process. But will detecting misnamed cities more effectively prevent this incident from ever happening again? Maybe not. What if the results of the failed evaluation are overridden by leadership? Maybe intentionally, maybe unintentionally. So this is a game of whack-a-mole, but instead of moles, you have the events in a chain. Another problem with the chain of events is how the events are selected. So this is subjective. Why is the event geospecialists miss states containing misnamed cities the root cause and not a previous event? What about geospecialists in New York lacks expertise to evaluate Washington? And so on. You can always add previous events and extend the chain indefinitely. That is, until you arrive at the original Big Bang event. So I challenge you all to backtrack through that and come up with events. So jokes aside, my point is that the choice of events from the incident is subjective. And this raises an important question. What is the stopping rule? How do we decide what the first event is? In other words, why is this particular event the root cause of an incident? Maybe the event is familiar to us. Maybe the event explains the incident in a simple way. Maybe we can think of action items that prevent this event. Or maybe we cannot backtrack through humans. Or we don't have information to go beyond a particular event. Maybe the event is convenient or politically acceptable. Maybe a previous event is embarrassing to the organization. Again, the selection of the events in the chain is subjective, including the root cause. Another major limitation of chains of events is that there exist causal factors that cannot be represented as events. These include systemic factors like management's decision-making, the safety culture of the organization, the management of change procedures, inadequate feedback and communication channels, changes in the environment outside the system. On one hand, these systemic factors cannot be included as events in a chain. And at the same time, the systemic factors have the most profound impact on the occurrence of incidents. And I will show you an example of that in a bit. Bear in mind that these systemic factors can crush all your Swiss cheese slices simultaneously. Now, let me change gears and show you what I meant earlier by an accident model based on systems theory. So here we are modeling adaptive behavior happening in the system in the form of control feedback loops. Our goal is to analyze how the system enabled unsafe decisions to happen. In a control feedback loop, the bottom box is the controlled process, and its behavior or state must be constrained. The controlled process could be hardware, could be software, even human components. The top box is the controller, and its goal is to constrain the behavior of the control process underneath. Like the control process, a controller is often either software or humans. The mental model of the controller is its worldview. It's a set of beliefs about the state of the controlled process. And the mental model of the controller is updated with the actual state of the controlled process via feedback, which we represent here via an upward arrow. And each controller makes decisions that affect the state of the controlled process when the mental model says that the controlled process is in an undesired state. This is its decision-making process. And the visible effect of this decision-making process are the control actions, which change the state of the control process and are represented by downward arrows. And sometimes these control actions can be unsafe, meaning that they result in an undesired state of the controlled process. And after the control actions update the state of the control process, the cycle starts again. And this loop models the adaptive behavior of the controller. Now, what are the causal factors that can lead to unsafe decisions? Well, there can be several of those, but the most common category of causal factor is an inconsistent mental model. What if the controller has the incorrect belief about the state of the control process? So this can lead the controller to make an unsafe decision. The inconsistent mental model can be caused by problems with the feedback. For example, there could be no feedback available, or the feedback might be incorrect, or the feedback might arrive late. We can analyze this loop to identify the controller's contributions to an incident that happened. And this is what we did with CAST and the misnamed series incident. So to summarize this section, lots of terminology, using an accident model based on systems theory, we move from a focus on preventing events that should have not happened to a focus on changing the system so behavior of decision makers is constrained to safe decisions. For example, if a particular feedback is required to make safe decisions, but we find that the feedback does not exist in the system, then we can design and implement that feedback. You can prevent all the events in the chain from happening, but there will always be new, unforeseen events that happen in the future. Postmortems based on root cause analysis have been part of Google's culture for a long time, done after every major incident for over 2 decades. And cultural changes are slow. The adoption of CAST is going to be slow. Let me show you the CAST analysis now. So the incident was not major, but it definitely had lots of learning potential. And as I showed you, a postmortem was done for this incident. Leadership had heard at the time about the CAST analysis that we ran on previous unrelated incidents, where we showed CAST found more issues than the postmortem root cause analysis. So I was asked to run a CAST for this particular incident. And I will show you now what I found with CAST so we can compare it with the RCA results. So remember the control feedback loop I showed you earlier? So this is a bunch of control feedback loops organized into a hierarchy. And we call this a control structure. And drawing the control structure is one of the initial steps of CAST. And this is the control structure of the system at the time of the incident. At the bottom, we have the maps database, which contains information about geographical entities, in this case, information about cities. The system must prevent this database from entering undesired states. For example, storing cities with incorrect names. And as I mentioned earlier, the geospatial team uses an evaluation tool and follows an import policy to try to identify and report problems in candidate datasets before importing them to the maps database. The dataset import team applies individual fixes to entities in the map during incident response and also establishes the import policy that the geospatial data specialists at the bottom must follow when they are evaluating datasets. And lastly, engineering responds to incidents by rolling back bad datasets and coordinating response with the dataset import team. So after modeling the system at the time of the incident with a control structure, the next step in CAST is to analyze the contributions to the incident of each individual controller. Let's see an example for the dataset import team. So remember that the dataset import team defines the import policy that the geospatial team must follow while evaluating a dataset. So what was the contribution of the dataset import team to this incident? So the dataset import team did not update the policy to enable detection of localized problems in the US Census dataset. How can we explain this decision? Let's look at the mental models. During the analysis, we asked this team involved in the incident. So you knew that the geospatial team would evaluate the US Census dataset. What did you believe about your import policy existing at the time? They told us that they believed at the time that the existing policy would detect any problem in the US Census dataset. This belief explained their decisions to not update such policy. Now, our goal as CAST facilitators was to explain how the dataset import team created that belief. So we found two factors. The first one was that the datasets that were evaluated and imported in the past were uniformly generated. This meant that if the datasets contained problems, those problems tended to be evenly distributed across all geographical areas. The default assumption was that the US Census dataset was also uniform. So if the 4 states they evaluated did not contain bad data, then the whole country would not contain bad data either. And the second factor, contextual factor, was that in the past, the team had imported other US Census datasets, but this was the first time that the US Census dataset included information for cities. So the team had low familiarity with this particular type of data. Now, if you look at the control loop counterclockwise, these two contextual factors influenced the mental model that the dataset import team had about their own import policy, which explained their contribution to the incident. Now, let's look at one contribution by engineering in the context of incident response. So engineering took a long time to roll back the US Census dataset. Now, some of you might have gotten a gut reaction like, isn't that blaming the engineer? So if we stopped here, then yeah, I mean, we would conclude that it was the engineering's fault, and that would be it. But there are two very serious problems with this. The first, we don't uncover the factors that influence this decision. This is somewhat irresponsible because we don't change the system to address those factors. And it's likely that a different person, a different engineer, working in the same system and the same situation will make the same unsafe decisions. And second, as an incident analyst, we probably damage the psychological safety of the team. Now, the good news is that we all here in this room, I'm sure, know better. So we assume that the engineers did their best to try to fix the problem as soon as possible with the information they had at the time. That's why we looked at their mental models and the contextual factors that influenced their decision. Initially, the engineering's mental model was that the US Census dataset did not need to be rolled back. Why that belief? For once, engineering didn't know the scale of the problem while the incident was ongoing. Were there a lot of misnamed cities or just a handful of them? Engineering knew that the dataset import team had started to apply manual fixes to the misnamed cities. Would these manual fixes be applied quickly to all misnamed cities? After a while, the dataset import team was still applying manual fixes, so the number of misnamed cities was still inconclusive. So engineering decided to initiate a parallel rollback of the dataset. And this caused database conflicts with the manual fixes, which introduced delays. The other contextual factor was that it was not clear when manual fixes or automated rollbacks should be applied during incident response. And this resulted from a diffusion of responsibilities during incident response. Remember, at the time of the incident, engineering didn't have the information we have today. So we now know that there were only 9 misnamed cities, but it was not possible for the engineer to quickly find out about that during the incident. And hindsight is a luxury of our future selves. So again, if you look at the control loop counterclockwise, these 2 contextual factors influence the mental model that engineering had about whether the data set required a rollback, which explained their contribution to the incident. So, but what about the systemic factors, those that have the potential to affect the entire control structure simultaneously? So after analyzing each controller individually, the next step in CAST is to analyze the control structure as a whole. The main systemic factor we found was changes over time in the environment, everything that was outside our system. As you can see in this picture, the size of the data sets the team received from different data providers had been increasing over the past years. And this had ripple effects across the whole system, weakening the existing controls. Let me show you this visually. From a control structure that initially handled small and medium-scale data sets effectively, in recent years, the data sets we received became larger and larger, and the control structure migrated to a state of higher risk, in which the existing controls gradually became weak at handling larger and larger data sets. All of the controllers in this control structure and the control actions were made ineffective. And you cannot generate insights about systemic factors when looking at the decisions of individual controllers. You must look at the entire control structure. That's why we have an additional step in CAST. Now, let's go on a brief tour of the areas impacted by the environmental systemic factor. The first was evaluation. The dataset import policies did not contain clear sampling rules for the evaluation because they were originally designed to evaluate entire datasets, which were manageable by the team in the past. And as we learned earlier in this incident, the team selected in an ad hoc fashion only for states that contain good data and didn't evaluate the data for the states containing misnamed cities. The second was the evaluation tool. The tool requirements were never reassessed over the years to address the detection of localized problems as the size of the data sets grew. And lastly, the incident response. The responsibilities during incident response protocols were not clearly allocated in situations where large data sets contain localized problems. So our objective with CAST is to formulate recommendations to enforce the safe behavior at both the component and the control structure levels. And for this incident, CAST found 22 recommendations. And here are just 3 examples of those. The first one was to redesign from scratch the data import policy to manage increasing volumes, using structured sampling rather than random sampling. To complement this, also establish a leading indicator of risk to monitor the effectiveness of the import policy so that we can identify when the import policy weakens and moves the system to a state of higher risk. The second example was to create individual probe alerts for frequently rendered map entities, not just series, to provide rapid notifications of changes in otherwise stable data. The third example is to implement a policy to notify dataset providers, for example, the US Census Bureau, of incorrect data and to recommend fixes to them. And despite the initial cost, in the long run, this improves the data quality and coverage for recurring imports, benefiting all consumers of public datasets. Now let's quickly compare RCA and CAST, examining both methods and the results as they were applied to this particular incident. This is not a general comparison between RCA and CAST as accident analysis methods. So for the underlying accident model, so the RCA found 2 root causes for this incident. CAST demonstrated that there were no root causes for this incident, only mental models, contextual factors, and systemic factors that influenced the decisions that contributed to the incident. The improvement plans reflected the nature of those findings. The RCA action items treated the incident symptoms, like fixing limitations of the evaluation tool or increasing people's diligence on top of the existing evaluation process. The CAST recommendations addressed the causal factors of the incident, acknowledging the need to make the control structure as a whole resilient to a changing environment. The frame of analysis was different too. The RCA focused on proximal events around the incident time, evaluation of the US Census dataset, the use of the evaluation tool, the import of data, the rollback of the dataset. CAST also, on top of that, focused on distal events. For example, we analyzed past incidents, which allowed us to identify the trend in the increasing volume of data over the years. Lastly, the organizational factors. So RCA focused almost exclusively on the technical aspects of this incident, with emphasis on the support of the evaluation tool. CAST went beyond the technical aspects and analyzed the interactions between the humans, like the Google internal teams and the US Census Bureau, and between the humans and the software components. Now, let me tell you my final takeaways. So at Google, we found that CAST is a powerful way to look at our incidents. We found that the insights from CAST go far beyond those of the postmortems that are based on root cause analysis. For example, while the RCA, in this case, focused on the symptoms like preventing recurrences of misnamed cities, CAST looked at the effects of the environment in the system over the years, revealing systemic factors such as the impact of growing datasets. These deeper insights allow us to make more impactful recommendations. For example, redesigning processes like the evaluation and the incident response, rather than just patching the existing ones. And at Google, CAST is getting us to where the postmortems based on root cause analysis can't. Just to wrap this up, a few resources. So from left to right, here is an article that we published in USENIX, describing how we are applying system safety engineering methods at Google. In the center, you can find the original CAST handbook published by Dr. Leveson from MIT. And lastly, in the upcoming second edition of the Google SRE book, we cover CAST in the Safety Engineering for Software chapter. And with that, thank you so much.